Okay, so yeah, so we have seen why an account-based or transaction-based ledgers, what are the advantages and disadvantages, right? So in case of cryptocurrencies, we go with the transaction-based ledger because it will allow us to do only finite verification checks. So that is the main reason, right? So then let us look into some Bitcoin transactions. The Bitcoin follows this double entry bookkeeping transaction. So what does it mean? I'm not an expert in accounting, but you have on one hand you have the inputs, on one hand you have the outputs. So basically, and then we follow the rule saying that the total value of the input should be greater than the total value of the output, right? Otherwise, it doesn't make sense. If I'm spending coins worth of 55, and then I can only create coins worth of less than 55, and then the balance will be the transaction fee, right? So in this case, we have 0.55 bitcoins and as inputs, and the total outputs is 0.50 bitcoin. So the 0.50 bitcoin is implied as a transaction fee and things like that. So now let us take a very simple use case scenario, right? For example, let's say that Alice want to buy a cup of coffee with with her Bitcoin or with her coins and things like that. How does she do it, right? So first of all, she need to have the coins. She need to buy the coins, right? So, or get the coins from somewhere else. So let's say that Alice met her friend Joe to exchange some cash for the Bitcoin. So that means she will create a wallet. Again, we'll see more about the wallets in the next lecture. But wallet is nothing but which holds the coins and things like that, right? So she provides her public key where the wallet is listening and things like that. Let's say that they exchange the fiat currency, and then in return, let's assume that Alice receives 0.1 bitcoins to her account. And now let's see how she buys a cup of coffee. She goes to a coffee shop and order a cup of coffee. And then while payment, she want to pay in the bitcoins, right? So the point of sales is automatically converts the value of the price of the coffee to the bitcoin. And let's say that it is 0.015 bitcoins. Let's say that coffee costs 1.5 US dollars, and it is equivalent to 0.05 bitcoin. Let's not look into the actual conversion rates and things like that. The Bitcoin price is now very, very high and things like that, right? So, but then how does the coffee shop receives the Bitcoins from Alice for the cup of coffee, right? So then Bob's point of sale system. So Bob, who owns the coffee shop, it will create some kind of QR code for transfer. So like this one, payment transfer, and she can scan this QR code, and which contains some information about the destination Bitcoin address to which the payment has to be made. So since the Bob owns the coffee shop, so the coffee has the payment has to be transferred to his public key or whatever the key, and some other information to mark the transaction. So, for example, a transaction, the QR code looks like this. So you have some information saying that Bitcoin, to which address the Bitcoin has to be transferred, amount of the Bitcoin, and label. So maybe the Bob's coffee shop and things like that. And then you have some message saying that for the purchase of the coffee and things like that, right? So what is this ugly the characters? So this is nothing but URL encoding. And if you have studied the web programming, so you cannot use spaces and other kinds of characters in the URLs. So that means what you have to do is you have to encode them into some characters. For example, here we have the Bob's Coffee Cave, right? So you can see here Bob's, and ampersand is the single quote is converted as 0.27 s, and then a space is converted as percentage with 20 and things like that. So these are the encodings which people will use in the URLs, because you cannot have spaces and other characters as part of the URL. Then it will be picked up the wallet by the Bitcoin wallet, and then it will carry that information. It knows that it has to transfer 0.015 Bitcoins to this public key, and then it will automatically done the transfers. And LS will use her smartphone to scan the barcode and authorize payment, and the payment is sent to the point of sale system. So now you can see here the whole transaction is represented like this. We know that Alice got coins from the Joe, who is our friend, in exchange of some dollars or something like that. So that transaction outputs 0.015 bitcoins to Alice, and then this is the transaction where Alice pays money to the Bob coffee shop, right? So she got 0.1 Bitcoins from the Joe, and this is the transaction fee, let's say, because you need to pay some transaction fee to make the transaction appear on the blockchain very fast. And when Alice got 0.10 Bitcoins into our wallet, and then she outputs a transaction. She creates a new transaction, transferring 0.015 Bitcoins towards the cup of coffee, again to the Bob's address, right? And then what she does is, remember we have these immutable coins. So that means the coins cannot be transferred or subdivided. So she had the 0.1 Bitcoin. She had a coin having a value of 0.1 Bitcoin. And then what she will do is she will burn this coin, and she will create two new coins, right? One coin with a worth of 0.015 Bitcoins, and this will be transferred to the Bob's coffee shop address, to that public key. And another coin which is created, which is transferred for the value of 0.0845 Bitcoin. This is transferred to her own another public key, which is controlled by LS, right? So again, why do you want to transfer to a new public key? Can't we transfer it to the LS's public key, existing public key, where she got the coins? You can also do that. But when we look into the anonymity of the cryptocurrencies, we always create new addresses and things like that. We'll discuss more when we come to the anonymity lecture. So, and in case of Bob, he receives 0.15 Bitcoins and things like that. Then he can transfer further, and he can split, and he can create and things like that. So, and again, there are different, so Bitcoin value is quite high. I don't know what is the price now, maybe $50,000, $60,000 or something like that. So then you also talk about the fraction of the Bitcoins, milli-Bitcoin. Satoshi is, I think, 100 million. You split the Bitcoin to 100 million, then it is called a Satoshi and things like that. And when we look into the type of the transactions, then there are two main types of the transactions, you can do two or three. So the first one is change address. We have seen this many times. Even when LS want to pay Bob coffee shop, so basically she's sent the 0.015 Bitcoins to Bob, and she sent the rest of the coins to herself, right? So basically by creating new coin. This is called the change address, which is very, very common form of it. And then you also have the aggregating funds. Let us say that you receive coins from different people, right? And then what you do is you can input them, all of them, into one transaction, and then combine them, and then you can output, you can spend all the coins containing the small amounts. Let's say this is 0.10 Bitcoin, this is 0.5 Bitcoins, this is 0.0025 Bitcoins and things like that, right? And what you can do is, rather than having all the coins with subdivisables, you can put them as input, right? And you can combine them, and create a new coin, transferring the almost the same value of the inputs, right? So then you are aggregating funds. So this is how your wallets will also work. Your wallets will receive coins from different places and things like that, but they show you the overall value and things like that, right? So this is equivalent to this is nothing but, let's say that if you have a lot of change, physical coins, like half a rupee coin or the 1/4 of a rupee coin and 1 rupee coin and five rupees coin. This is like collecting all the change and maybe going to an ice cream shop and buying ice cream, right? So something similar to that. So this is how merging happens. Then we look into the transactions and things like that. So now let's say that you have Bob receives two inputs. So in the first transaction, Bob has 17 coins. And in the second transaction, Bob has received two coins. Now let us say that now Bob want to match these two coins and output one single coin. So what he will do is he will input those two coins, two coins. So how he got the money, 17 coins here, and this is containing two coins worth and things like that. And then he will simply output to a address which is controlled by him. Similarly, joint payments also. Joint payments is another scenario. Let's say that you have two people involved in the transaction, right? So let's say that Carol and Bob, they are partners in a business and things like that. Now they want to pay David 23 bitcoins. And then what they do is they will simply list out all the coins which they have. So for example, 20 is the Carol getting 6 coins, and 10 is Bob getting 17 coins. So they will input them. But here one important thing is everybody has to sign. So both Carol and Bob will sign, and then this transaction is valid. This is completely different from multi-party signatures. We will also discuss multi-party signatures a bit in the next coming lectures or something like that. Okay, so how actually a Bitcoin transaction look like? So a transaction contains 3 important pieces of information. So transaction header, you can say. So this is the metadata. Hash value of the transaction, version, number of inputs, number of outputs, lock time, we'll discuss later, but size. And then you have a series of inputs and a series of outputs. Similar to what we have seen here, right? You have the inputs. For example, you have a series of inputs and you have a series of outputs. So similarly, the transaction also, actual transaction also contains the series of inputs and the series of outputs. So let's go a bit detailed, right? So what is metadata? Metadata contains, first of all, a hash value of the transaction, right? So again, remember we use hash pointers because we want to make sure that tamper resistance property and things like that. So we have hash pointers and things like that, but it contains some important information. It contains version. This is like a some kind of protocol version and things like that. But V in underscore SZ is nothing but the size of the inputs. So in this case, we have 2 inputs. You can see here, one input, and this is another input. So so the header will contain saying that 2 inputs. Similarly, the number of outputs, V out size is number of outputs. So how many coins we are creating, and this is how many coins we are spending. Lock time, let's wait for the lock time until some lectures. So we will discuss this more in the coming lectures. So it is some kind of lock you put on the transaction and things like that. And then you have the size of the transaction, which is in bytes and stuff like that. So And then how does the input look like? So input starts with the syntax. So basically, you can say that this is a JSON structure, right? So when you have a transaction, I will also show you a real transaction and things like that. And basically, it is in the form of hexadecimal format and things like that. You unpack them and put it into JSON format for human readable purpose and things like that. So it contains two inputs, as we mentioned. So each input contains some information. So now we are unpacking the inputs. Remember, we need to give the pointer to where the coin has come from. So this is the previous out. So basically, this is the pointer to the previous transaction where we get the coin. So the hash value of the transaction ID and the serial number of the coin. So let me go back one step. So you can see here, for example, this is the input. We say that 20. So that means the transaction ID 2 and the first coin. So similar to that, what we have here in this case is also, what we have here is also the same thing. So the hash value of the transaction where the coin is transferred to this person, and the serial number of the output. So N0 means this is the first output from the transaction. So basically, this is a reference pointing back to the transaction where it is created. And remember that we need to sign the transaction. Remember that the owner of the coin has to sign the transaction, right? So this is the signature. So this contains a series of bytes. And we will also see when we get back to the Bitcoin scripting, how do we actually verify a signature and things like that. So we use the scripting language, Bitcoin scripting language, and then we do a fast verification and things like that. So, and this is one input, and you can have multiple inputs. So this is an array, so any number of inputs are possible, and things like that. And the output also looks a bit similar. So basically, remember that what we have in the outputs is the address to which a coin is created and the value of the coin, right? So if you go back here, so outputs contain the value and to whom it is transferred, right? So similarly, the output also, in the Bitcoin output also contains the same things. So here we have the output value. So the number of coins we are creating. So we are saying that it's 10.12 228 Bitcoins we are creating. And then we have the public key to which the coin is transferred. Ignore this horrible syntax will also come when we look into the Bitcoin scripting. So basically what we are saying is we are transferring this coin to the recipient's public key. This is the public key which we use. And these are the scripting operations. We will look more into after a few lectures and things like that. So this is basically, you can imagine that you have a public key and some extra information. Okay, so you can take a look at the Bitcoin raw block. So let me open this. Then I have to stop share and share it back again. So you can see here, So the raw data looks like this. So basically, you have most of the things are in the hexadecimal format, right? So the hash value in the hexadecimal format, you can see here A, B. You people know what is hexadecimal, right? So basically, we encode the characters using hexadecimal format. So this is how hexadecimal format looks. And then you have some reference and other kinds of things. Okay, let me put it to JSON form. So this is the whole block, the whole block containing this. This is the block ID and things like that. So you have some extra information on the block, but let me go to the transactions, right? Because this is what we focus now. So you can see here, we have some transaction information, hash value of the transaction, and the version, protocol version, and the number of inputs, one coin, and the number of outputs, three coins, and size, and some extra information, and lock time. This is what we have discussed. And some other additional information which is being introduced in the latest versions of the protocols and things like that. But the important thing is this input, right? So we have seen that one input. So we have one input value, and you have the previous output. So this is the point to the hash value, and then lot of other information, right? So, and then you will have signature. You can say the witness is nothing but the signature, right? In the simple terms, imagine that witness is nothing but the signature who transferred this coin to this person, something like that. And it could be also like much more advanced. And the recent versions of the Bitcoin proposal, it contains the signatures and things like that, because you can use for the advanced functionality and things like that. But for the just time being, you can think that this is a signature of the owner of the coin transferring and things like that. Okay, let's look into the output. We should have three outputs, right? So as this indicated, three outputs. So let us see. This let's see output. So you have the three outputs. So the first coin is created a value of this much, and and the value is 0, and so this might be some kind of create coin transaction. We can also look into the other things. So here we have one input and one output, and so basically the same format which we have. Any questions or comments? The value here, it is Satoshi's, which is represented the fraction of the Bitcoin and things like that, right? So, okay, so let's move back to the slides. So I was saying that witness and things like that, right? So witness is nothing but witness is nothing but some kind of signature, but it could be a collection of signatures, right? So when you have the multi-party signatures, and we also look into the aspects of the executing at the hash of a script and things like that, script execution and those kinds of things. There are several complicated scenarios where you don't have a single signature, but on the other hand, you can have a series of signatures and things like that. So that's why the witness and the segregated witness, this is introduced. And if you want to more information, you can find it here. And this book is available online, and so Mastering Bitcoin and things like that. And it gives you a detailed description of what is a witness and what it contains and things like that. Okay, so let's look into the block structure. So basically, as I was telling you before, its block structure is nothing but you have the blocks, and then you have the hash pointers between the blocks to make it, how can I say, make it append-only ledger and tamper-resistant ledger and things like that. So what we do is, when we create a block, we put all the transactions and we form the Merkle tree. And then we put some additional information about the header. And then we take the parent block to which our block will point, take the hash value of it, and put it here, right? So this is how the hash pointing linking works. So it contains a lot of extra information. So for example, it contains the block header hash. So first of all, it contains a hash value of the block, right? So this is the hash value of the block. And then you have the height, which is nothing but the current serial number of the block, you can say, and the size of the block, and some block header information, and the series of transactions you have. So basically, if you look into the structure of the block, it contains a block size, which is 4 bytes, and you have the block header, which is 80 bytes, contains several information, and then you have the transaction counter. So how many transactions will follow, and then you have variable size of transactions. So all the transactions put into the Merkle tree and also enclosed into the block, and things like that. Similar to what we have seen here, right? So all that information is represented. And let's look into the block header, because this contains some important information, which we'll also see in the further lectures when we want to do the mining and other kinds of things, how Bitcoin mining works, and how the hash value of the block is created, and those kinds of things. So at that point also, we will look more in information into depth. So the structure of the block is like this. It contains a version, and it contains what is the previous block hash pointer. So this is the hash pointer, and it contains the hash value of the Merkle root. Again, remember, the Merkle tree is a hash structure. If you take the root value of the root hash value of the root of the Merkle tree, then it guarantees that all the transactions in the Merkle tree, they are unchanged, tamper resistant property. And timestamp and difficulty of the target. For the time being, just let's postpone this till we come to the mining lecture. So this is the difficulty which the miners have to fulfill to create a block, right? So for the time being, just ignore it, right? And then we have a nonce, which is a counter, which will be used by the miners to create the block with specified difficulty. So to be in a layman terms, what is the difficulty? So basically, it says that the block, the hash value of the block. Again, what is hash value? You take all the data in the block, ignore some headers and things like that, and you compute the hash value of the block, including all the transactions and things like that. And the hash value of the block should contain this format. So that means you need to have, for example, 17 predefined zeros in the hash value. As we will see a bit later, hashing provides some strong properties against the puzzle fundiness and other kinds of things. So there is no way for the people to create this hash value except keep on trying. So that is referring to the hash difficulty, how many number of zeros you need to have in the hash value and things like that. For doing that, people will manipulate these nouns. So you will implement these nouns and things like that. So if you look into how a block look like, let me open this. Yeah. So this is how a block look like. Again, you have the block, which is most of the data is in the hexadecimal format and things like that. And you will unpack the block. And then what you do is you can show it in a manner like this, right? So this is the hash value of the block, and this is the height of the block. So they basically this is nothing but the block is the serial number of the block is 775933. So you can see that height is 775933, and the next block is the same serial number 775933. 5934, and previous block is 775932, right? But the Merkle root, so the root of the hash value of the whole Merkle root containing transactions is included, and the size of the block and the version, bits is not size of the block. Bits is again refers to the difficulty of creating the block, again, which boils down to how many number of zeros you have, and this bits field is something related to that. Again, I will talk about these things when we come to the mining part, and how the bits are related to the difficulty and things like that. So difficulty means this is the number of, you can say, number of trillions of transactions you have, trillions of times you have to try to get this hash value and things like that. But you have some auxiliary information saying that number of transactions. So for example, this block contains 2,700 transactions and things like that. Block reward. So how many Bitcoins are created as part of the block? You can say that it is 6.464. Why it is so? The current reward is 6.25 Bitcoins whenever you create a new block, and the rest is the transaction fees collected from each transaction. So that's why you have this figure, total figure, more than the block reward. Right? 6.25 is and these are the transaction information. So you can also go through it, and the number of confirmations, how many miners have confirmed and things like that, and some transaction details and other kinds of information. Okay, so let's switch to, again, we will be visiting this block structure and internal details of the Bitcoin block structure more and more, right? When you come to the scripting also, we'll again look more into the in-depth and things like that. Okay, so this is the Genesis block. This is the block which was created in the first time. And I was also mentioning that there was some information put into the Genesis block. So yeah, sorry. So it contains all these structures. And when we come to the much more in-depth scripting, I will also show Nakamoto how he put the information into the Genesis block and things like that. Okay, so how the blocks are linked. So this is how the linking happens. You have the hash value put into the next block and things like that. Okay, so let's, any questions so far? Or comments?
No, sir.
Okay. So let me quickly go through the hash functions, right? Most of the cryptocurrencies or blockchain is built on the hashing. The reason is hashing offers some beautiful properties. So the whole foundation is built on the hashing because of its beauty of the hashing functions and things like that. First, let me talk about what is hashing. Hashing is, it takes any arbitrary input. So the data could be any data, but on the other hand, it will produce a fixed output. So for example, here we have input fox. If you hash it, you will get this one. You have a sentence called red fox jump over the blue dot, and then you get this hash value. Same fixed digest. Let's say 256 digest, right? Let's imagine that you change a small character. For example, here we have the red fox jump over the blue dot. And here we say that red fox jump over, in place of V, let me replace U, right? And then the hash value will completely change. You can see here there is no relation between these hash values. It's completely new hash. You will get a new hash value. So that means the hash value will make sure that if offers a guarantee against the tampering of the data, right? Because if you change a single bit, then the hash value will be totally changed. And again, it's efficiently computable, so you can easily compute the hash. For example, if you have your laptop, I think it can produce easily 10,000 to 100,000 hashes per second. So that is the efficiency of computing a hash value. And most of the cryptocurrencies, even Bitcoin and other kinds of things, they use a 32-bit hash value, which is common, quite common on our computers and things like that. And again, one of the basic design goals for the Bitcoin is that people can mine the whole Bitcoin on their laptops. But that's not the case now. But we'll discuss more of those things when we look into the mining semantics. But hashing offers some beautiful properties. The first of all, it is collision-free, and it is hiding, and it is puzzle friendliness. So these are the three properties it offers. I will talk about them, what it is and things like that. So again, hash functions, they belong to cryptography. So different types of hash functions we have. But when we talk about hash functions in case of cryptocurrencies, we always talk about cryptography hash function. So this is a one-way function. So that means, let's say that if you have a value y, you can hash it. You can find the hash value of it. Sorry, you have a x, then you can find the hash value of it. And if you only have the hash value, you cannot get back. So that means using the hash value, you cannot easily identify what is the original value. And then we have also pre-image resistance. So that means two data values, they cannot have the same hash value, and also collision resistant. Okay, so yeah. And again, it property satisfies some of the properties, saying that pre-image resistant. It should be infeasible to find the input A contains the hash value. So that means what it means is, if I give you a hash value, it is nearly impossible to find what is the original value, right? So again, why it is difficult? So for example, you can see here, we have the hash value, but on the other hand, using the hash value, there is no function which will take back us to the original value. These are one-way functions, right? So you cannot get back to the original value. So that's the one thing which it offers. And the second important thing is deterministic. So hash always produce the same value if the data is the same, right? So again, what does it mean? So for example, if I use the same text, no matter what, if I send it, create hash value for 1,000,000 times, I will also get the same hash value, right? So the hash value doesn't change. So that is the deterministic property. And unique property. So what does it unique property means? So that means there is, if you have, so unique property guarantees that no two values can have the same hash value, right? So that means the hash value is always unique. That is what it says. Let's look into these properties, right? Collision-free, hiding, and puzzle friendliness. Because of these three security properties, hashing is used as a foundation for cryptocurrencies. First, try to understand what is collision-free. What is collision-free? So what we are saying is, nobody can find X and Y such that the hash value of X and hash value of Y is the same, right? So what we are saying is that you cannot find two data values, two input values for which the hash value is the same. So that is the collision-free property guarantees. But again, let's imagine what is hashing. What we are saying is, on left-hand side, I have all the possible inputs. Remember, hash function takes arbitrary input. So that means you can pass pretty much any amount of data. It could be 2 bytes of data, it could be 2 terabytes of the data, or it could be 1 megabyte of data. So all the possible inputs in the universe could be the input for the hash value function. But what is the output of the hash value function? We have seen that if you use SHA function, SHA-256, the output is a fixed digest. What I mean to say is, you have a fixed number of values to which this infinitely huge amount of data is being mapped, right? So you see the contradiction here. So on one hand, you have all the possible types of inputs, like let's say this is infinitely many infinite possible combinations, which are being mapped to the 2 to the power of 256. The number of values we have here is because it is a 256-bit hash value we are looking into. So the total number of the values you can have is nothing but 2 to the power of 256, right? So on one hand, you have infinitely many values, but on the other hand, you are mapping them to a smaller domain. You can say a smaller space value. So definitely collisions exist, right? So definitely there will be a lot of values for which we have the same hash value. But the beauty of the hash functions or the implementation of the hash functions is that it is very difficult to produce a collision, right? So for example, if you use a SHA-256 function and you need to try at least 2 to the power of 130 times, then you have a chance of getting 99.8% chance to get two items will have the hash value, the same hash value. So what is this big number? If you try to combine, let's say that whether it's possible to produce a collision or not, right? So let us take that we get all the computing power in the world, or you can say in the universe, and then we use all the computing power and keep on doing the hashing. Even then, we might not able to produce a collision, for example, in 1 million years or something like that. So that means it is possible to get a collision, but on the other hand, the probability of getting a collision is very minimal. So that's why we say that it's absolutely, it's not absolutely collision free, but it's practically collision free. Okay, so how do we use this the collision free property? Because we have seen that it is very difficult to produce a collision. So we can, so for example, let's say that I have a pretty big file, right? So which I want to store on some cloud sourcing, cloud data structure or something like that. And then I put it on, for example, let's say I'm uploading a huge file to the Dropbox and things like that. And then what I can do is, rather than keeping save of all the huge data, I can take the hash value and I can store the hash value. And then when I download the file again, then I can check whether the hash value of the downloaded file and the version hash value, if both the hash values they match, the file is intact, not touched by anyone, or you can say the file is tamper proof. So rather than keeping the whole the data file, you can just take the hash value and then you can save it, save only the hash value, because having a hash will guarantee you that nobody else can change the file. If they change the file, you can easily identify. So that is the reason why we use hash pointers, because if somebody changes even a single bit, the whole hash value will change. So that means when somebody tampers data in the block, the hash will change. So this will break the hash pointers. So that's why we use hashing as a foundation for cryptocurrencies. The second thing is hashing offers hiding property. What does it mean? Let's say that we have, now we are in a space of online lottery, and we take a very simple game, tossing, right? So let's say that somebody is conducting tossing a coin and I'm betting on the coin, right? So then you can say heads or tails, but let's say that this is communicated over internet and things like that. So rather than passing the message, you can hash the values and send it. Remember, if you only have the hash value, you cannot really get back to the original data. So you can simply hash the heads and tails, and you can use it in the lottery and things like that. But again, if there are only two outcomes, if somebody is observing this communication back and forth, then he can easily identify what is heads and what is tails, right? If he also have access to the outcomes of the coin toss and things like that. So some eavesdroppers, if he communicates, if he observes this communication over the time, he can easily make a prediction, because how can I say, the number of possible values is very true, and the heads and tails, so somebody can guess it. What we do is, we do a simple trick. So for example, let's say that you have a message like heads or tails, which you want to communicate. And to be more secure, what you do is, you will take a key, random key, which is selected with a high mean entropy. What is high mean entropy? In the simple terms, let's imagine that you have a pretty huge possible values. Let's say that you have a trillion numbers, right? You have the numbers from 1 to several trillions, and you pick one value randomly, right? So basically, trying to choose a value from a very huge large database, right? So that is called high mean entropy. So let's say that you got this is your message, head and tails, and now you want to make sure that nobody else can find it. So what you do is, you choose a key from a big mean entropy, and then you can combine your message and key, and you take the hash value. And then if you pass this information, and then people cannot easily find it. The reason is, you cannot produce the hash with the same kind of random number. So that's why it is also used as a commitment. So what is a commitment? You choose a value. For example, in this case, let's say that you have head or tails. Then you choose one outcome, because in the betting you have to choose one outcome, right? Let's say that I choose heads, and then I seal it, right? So I choose one outcome and put it into a sealed cover, and then you commit to that value. And when the lottery is over, then what you can do is, you can reveal that what you have chosen, right? If it is heads, I have chosen first, then you will get the lottery. Otherwise, if the outcome is different, then you will lose money and things like that. So this is a normal commitment schemes which you use, right? So what we do is, let's again imagine that we have a commitment. So we choose a message, which is nothing but head or tails, and we choose a key. Again, key is nothing but we choose a random number for the big pool of numbers, right? So we combine them and we create a commitment, right? So, and then once I have a commitment, I will send it to the lottery person saying that, okay, see, I made a commitment. So that means I have chosen an outcome, either head or tails. I don't reveal it to you at this point of time, but I have made my choice, right? So this is like a choosing one outcome, putting into a sealed envelope, right? Let's seal it. We will reveal it later, something like that. So the commitment message is the one which is sent to the lottery person, right? And then let us say that the lottery is completely over. Now there is an outcome. Then let's say that I have chosen heads. I need to prove that I have chosen heads before the lottery, right? So this is the verification. So what I do is, I will reveal the message saying that heads, and I will reveal my key. And if I am honest, then people can see that they will put the message and they will put the key and they will hash it, and then they will see if they get the same commitment, then the value is right, right? So the reason why this commitment API works is, one of the properties of the hash value, we have seen this one of the security properties, right? It is nearly impossible to find exactly the same two values, for example, key and message, different values of key and message, so that it will produce the same hash value. What I mean to say is, let's say that I have chosen heads at the commitment time, and I choose some key, and then I create the commitment and give it to them, right? Now I have seen that the outcome of the lottery is tails, right? So then I want to, okay, I can see that I lost, but I want to cheat them, right? So then what I will say is, no, you only have my commitment, right? Now I will change the message to tails, and I will find another key which will give the same commitment value. So what I mean to say is, when I change the message to message prime, which is heads to tails, and then I can find key prime, so that it will give you the same commitment, same hash value. To do that, it is impossible in the hash functions. So that means, because we have this collision-free and pre-merge resistance properties guaranteed in the hashing, so for example, even if I want to cheat, I want to change my commitment, selection from heads to tails, I cannot find a key which will satisfy this property of giving the same commitment. Did you understand what I mean to say, or is it complicated? It gives two important things. On one hand, so again, ignore all the API and other kinds of things. Let's see how the commitment works using the simply lottery system. Somebody is tossing a coin on the other hand, and I have to make a selection whether I want to do heads or tails, right? So what I do is I choose one of the outcomes, head or tails. I choose a key because I want to, nobody want to guess it. So let's say that I choose heads. I choose a key. I put together these two values, and I will hash it. And that is the commitment. I simply pass this commitment to the holder of the lottery and say that, yes, I have made my choice, right? At this point of time, the lottery owner will only have my commitment, right? Again, is it possible to see what I have chosen from the commitment? No, because it's a hash value. He cannot see what is the original value, but he will keep my commitment. Then, after the lottery is drawn, then I have to prove my commitment, saying that, okay, let's imagine that there is a heads on the lottery. Then I will say that, okay, you can see here, this is the heads which I choose, that is the message, right? And this is the key which I use. So you can see, you can use these two things to verify my commitment. If I am honest, if I made the heads before the lottery, and if I use this the proper key, and the people can put together these two things, and they will hash it, and if they get the same hash value as same as the commitment which I provided before the lottery, then my commitment is valid. On the other hand, if I want to cheat, I can change the message, but on the other hand, I cannot find a key which will satisfy this property and give the same kind of hash value. So if I cheat, and if I say that I chose tails, and then people can easily put these two things together and hash it, and the commitment will not match, the hash value will not match the commitment. So then it clearly shows that I have cheated, right? And yeah, we can see that we are running out of time. Should I stop, or I have few more slides?
Sir, can you tell how many more slides are there?
Just let me see. Maybe 7, 8 slides. So should we take it next time?
Yes, sir. I think that would be better.
Okay, okay. Let's stop it, right? So let's stop it and then let's see, because understanding hashing is quite important because a lot of foundations are built over the hashing, right? Like the puzzle friendliness and why somebody cannot simply create a block with the target thing, and these are important. So let's stop here and continue next time. Okay. Okay. Have a nice rest of the week.